Hello, everyone, and welcome to the Environmental Science and Engineering Podcast channel. You ever think about those little everyday things that bug you? Like when you're trying to get a good lather going with your soap and it just won't cooperate? Or maybe you've noticed that weird white chalky film that seems to magically appear on your shower head? Yeah, well, today we're going deep on one of those kind of mysteries, hard water.
That's refreshing.
Well, maybe not literally refreshing, but definitely interesting. We've gone through a bunch of information definitions, causes, the effects you see every day, even some ways to deal with it. Our mission for this deep dive, to give you a clear picture of what's going on with hard water and why it even matters to you.
It definitely matters.
Right. And I bet a lot of you have already seen the signs, the ladder struggle, the scale buildup. Maybe your laundry feels a bit stiff sometimes. Well, we're going to connect those dots today. And at the center of it all are these tiny little culprits, calcium and magnesium ions hiding out in your water.
Exactly. Those are the main players. So let's break it down. What is water hardness, really? In simple terms, it's water's ability to make soap, kinda. Well, not work right. You know how sometimes you just can't get that nice bubbly lather when you're washing your hands or the dishes?
Yeah, it's like the soap is fighting back.
Right. That lack of lather, that's often your first clue you might be dealing with hard water. And like you said, the usual suspects behind this are dissolved calcium and magnesium ions. Now, there are a few other trace elements out there that can technically contribute things like aluminum or iron, but they're usually in such tiny amounts that they don't really make a difference. So for all practical purposes, when we're talking hard water, we're really talking about calcium and magnesium messing with your soap's ability to do its job.
So basically, these calcium and magnesium ions are the root of all this soapy evil. Okay, now our sources mention something called temporary and permanent hardness. What's the difference and why should we care?
It all comes down to the different chemical forms these minerals can take. Temporary hardness, sometimes called carbonate hardness, is specifically caused by calcium bicarbonate and magnesium bicarbonate. Now, the key thing about temporary hardness is kind of in the name. It's temporary. You can actually get rid of it just by boiling the water.
Oh, interesting. So is that what that scaly stuff is in my electric kettle?
It could be. That's often temporary hardness deciding to solidify as the water heats up. So understanding this difference might even explain why some kettles seem to get that scale build up faster than others. It all depends on the mineral makeup of your local water supply.
So that white stuff in my kettle isn't just some random gunk. It's actually temporary hardness becoming solid again. That's good to know. Now, permanent hardness sounds a bit more, well, permanent. What's the story there?
Permanent hardness, also known as non-carbonate hardness, is caused by different types of calcium and magnesium salts, things like sulfates, chlorides, nitrates. And as the name suggests, it sticks around. Boiling won't get rid of this type. The chemical bonds in these compounds are stronger. You need different methods to break those apart and actually remove the minerals. So if you're seeing that soap scum or scale even after you've boiled the water, chances are you're dealing with the more stubborn, permanent kind of hardness.
Got it. So boiling my kettle won't solve all my hard water problems. The permanent stuff needs a different approach. Makes sense. Okay, so we know these tiny little ions can cause some real-world headaches. Let's get into the nitty-gritty of those annoyances. I think everyone with hard water has experienced that frustration of using way more soap than they think they should. Why is that? Why does hard water make us use so much more soap?
It's all about the chemistry, really. The calcium and magnesium ions in hard water love to bond with the fatty acids in soap. When they meet, they form what's called an insoluble precipitate, basically a solid scum. So instead of your soap doing its job of making those lovely cleansing suds, it's busy reacting with the minerals in the water, forming this residue. And that's why you end up needing way more soap just to get a decent lather going.
So not only are we getting less lather, but we're actually spending more on soap because of these pesky minerals.
Exactly. And there's also the potential environmental impact of using more soap, more chemicals going down the drain. It's a double whammy.
Yeah, not good. And then there's the one that probably makes a lot of homeowners cringe. Boiler scale and lime scale. That chalky buildup you see on faucets, shower heads, it's more than just ugly, right? What kind of damage can it actually do?
Right. It's more than just an eyesore. When you think about it, the scale buildup can really affect your household systems. Hard water, especially when it's heated, encourages these calcium and magnesium compounds to come out of solution and form that hard, crusty layer limescale. This can build up inside your hot water pipes, your heating systems, and especially your water heaters. And the results? Well, first, it can clog up your pipes, reducing your water pressure and potentially leading to some expensive plumbing repairs down the road. Second, that scale acts as an insulator, meaning your heating systems have to work harder to do their job. Your water heater has to use more energy to heat the same amount of water. And what does that mean? Higher energy bills. So dealing with hard water isn't just about having shiny faucets. It can actually save you money and prevent some major headaches in the long run.
Definitely something to consider for the household budget. Now, what about our appliances, washing machines, and dishwashers? Our sources mentioned hard water can cause issues there too.
Unfortunately, those appliances aren't immune to the effects of hard water either. In washing machines, those mineral deposits can actually get trapped in your clothes, making them feel stiff and rough, not to mention not as clean as you'd want. Over time, this mineral buildup can also wear down the fabric, making it fade or break down faster. And in dishwashers, hard water is often the reason you see those pesky white spots and films on your supposedly clean dishes and glassware. But even worse, it can cause scale to build up on the heating elements inside the dishwasher, making it less efficient and potentially shortening its lifespan. Again, it's those calcium and magnesium ions solidifying, especially at higher temperatures, and messing with our appliances.
It's like these microscopic minerals are on a mission to make our lives harder. So
Yeah.
how do we figure out how hard our water actually is? Our sources talk about the WHO, the World Health Organization, having a system for classifying water hardness based on calcium carbonate levels. Why calcium carbonate? And how does that help us understand the hardness factor of our water?
That's a great point. Even though the hardness is caused by calcium and magnesium ions, we often express it in terms of an equivalent concentration of calcium carbonate, CaCO. It's kind of like using a universal language. This gives us a standardized way to measure and classify water hardness, no matter the exact amounts of calcium and magnesium present. It's a unit everyone understands in the water world.
So it's like a standard measuring stick for the hardness factor. That
Mhm.
makes sense. Now, this next one sounds a little tricky. Pseudo-hardness. What's that all about?
This is where water chemistry gets a little sneaky. Pseudo-hardness is when water acts like it's hard. Soap doesn't lather well, but it's not actually because of high levels of calcium and magnesium. Instead, it's high concentrations of sodium ions, NaO, that are interfering with the soap. Sodium doesn't form those classic insoluble precipitates like calcium and magnesium do, but in large amounts it can still prevent those nice stable suds from forming.
So you might see that poor lathering and think, oh, hard water. But the real culprit could be too much sodium.
Exactly. It's like a hard water imposter.
Love it. Okay, so we've covered what hard water is and the problems it can cause. But what can we actually do about it? Our sources mention a few different ways to remove this hardness. Let's start with the lime soda process. Sounds like something out of a chemistry lab.
It's been around for a while, but it's still relevant, especially for treating large amounts of water. The basic idea is to add specific chemicals that make those calcium and magnesium ions solidify and fall out of the water. For temporary hardness, which remember is caused by those bicarbonate compounds, we add calcium hydroxide, that's the lime, which triggers a reaction that forms insoluble calcium carbonate. That calcium carbonate settles out and we can filter it away. And remember how we talked about boiling water to get rid of temporary hardness? That's basically achieving the same thing on a smaller scale.
Okay, so that's for temporary hardness. What about tackling the permanent kind using the lime soda process?
For magnesium sulfate hardness, we also use lime, which leads to magnesium hydroxide precipitating out. And for calcium sulfate hardness, we use soda ash, that's sodium carbonate, which causes calcium carbonate to precipitate. So the lime soda process is all about targeting those different types of hardness with specific chemicals
Yeah.
to basically grab onto those calcium and magnesium ions and turn them into solids that we can then filter out of the water.
So it's like a targeted chemical attack on those hardness minerals.
Yeah.
Our sources also mention nanofiltration and ion exchange as ways to soften water. How do those work in a more practical sense?
Nanofiltration uses membranes with incredibly tiny pores that can filter out divalent ions with a double positive charge, like our friends calcium and magnesium. Smaller ions and water molecules can still pass through. It's a physical separation based on size and charge. Ion exchange, on the other hand, is a chemical process. We pass the hard water through a special resin that's loaded with sodium or potassium ions. The calcium and magnesium in the water are more attracted to the resin, so they basically swap places. The resin grabs the hardness ions and releases sodium or potassium into the water. This is how a lot of home water softeners work, actually.
So it's either physically filtering out those minerals or chemically swapping them for something less troublesome for our soap.
Got it. Now, how do we actually measure how hard our water is? Our sources mention some pretty high-tech methods like the atomic absorption spectrophotometer and EDTA titration. Those are the tools of the trade for water chemists. An atomic absorption spectrophotometer is a fancy piece of equipment that measures the concentration of specific ions, like the individual levels of calcium and magnesium, in a water sample. It analyzes how those ions absorb light at very specific wavelengths, so scientists can get a very precise breakdown of what's in your water.
Yeah, that's pretty impressive. And what about EDTA titration?
EDTA titration is more common and relatively simple. It's used to figure out the total hardness of water, the combined concentration of calcium and magnesium. EDTA stands for ethylenediaminotetracetic acid, which I know is a mouthful. Basically, it's a chemical that loves to bind to calcium and magnesium ions. And the clever part is, it uses a color change to tell us how much hardness is there. We use an indicator dye called chromium black tea, and we usually do the test in a slightly alkaline environment. When we add the indicator to hard water, it forms a wine red color with the calcium and magnesium ions. Then, we slowly add a solution of EDTA. The EDTA molecules grab onto the calcium and magnesium ions, kicking off the indicator dye. And as we add more EDTA and all the calcium and magnesium is bound up, the solution changes from that wine red to a distinct blue. By measuring how much EDTA we needed to get that color change, we can calculate the total amount of calcium and magnesium, and therefore the hardness in the water sample.
So it's like a color-coded signal that tells us how much hardness we're dealing with. Pretty neat. Now, where does all this hardness actually come from? Our sources mention natural resources like rocks and soil, but also industrial and domestic wastewater.
Let's look at the big picture. The main natural source of water hardness is the interaction of water with geological formations that are rich in calcium and magnesium. Think limestone, which is mainly calcium carbonate. As rainwater and surface water flow over or seep through these formations, they naturally dissolve those minerals, picking up calcium and magnesium ions along the way. That's why the type of rocks in a region is the biggest factor in how hard the water is. Now, beyond natural sources, industrial wastewater can also contribute to hardness. If those discharges contain a lot of calcium or magnesium salts from industrial processes, that can increase the hardness of the water they flow into. And even our own domestic wastewater from our homes can contribute. Things like cleaning products and other household chemicals that we use can contain higher valence cations, including calcium and magnesium, which end up in the water system.
It's interesting that our sources contrasted this with soft water, which is often found in areas with volcanic rocks. Why is the water there usually softer?
That's because different types of rocks react differently with water. Volcanic rocks, unlike limestone, are generally much less soluble. They don't dissolve easily, so they don't release a lot of calcium and magnesium ions into the water. That's why areas with volcanic geology tend to have naturally soft water. And our sources also pointed out that rainwater itself is naturally soft. It hasn't had much contact with those mineral-rich formations to dissolve them. So any trace amounts of calcium or magnesium in rainwater are usually insignificant in terms of hardness.
So the geological history of a place really determines whether you'll be battling hard water at home. Fascinating. Now, a lot of people worry that drinking hard water might not be good for their health. What's the science say about that?
It's a valid concern. But despite what some people think, the current scientific evidence doesn't really show that drinking hard water is harmful for most people. There's actually some research suggesting a possible connection between drinking moderately hard water and a lower risk of cardiovascular disease. This might be because of the intake of essential minerals like calcium and magnesium, but it's important to say that this research is still ongoing and the findings aren't conclusive. So while hard water might cause those everyday annoyances we've talked about, like a slightly different taste or some effects on cooking, it doesn't seem to be a health risk in itself.
That's good to know, more of a household hassle than a health hazard. Speaking of hassles, let's get back to the laundry room. Our sources really highlighted how hard water can affect our clothes.
Yeah, this is where hard water's effects are pretty noticeable. The calcium and magnesium ions can really mess with laundry detergents. They react with the surfactants in the detergent, forming those insoluble scums we talked about earlier, which basically makes the detergent less effective. So you need to use more detergent to get your clothes clean, and even then, you might not get rid of all the stains. And on top of that, hard water can leave mineral deposits on your clothes, which is why they can feel stiff, especially towels and cotton items. These mineral deposits can also make fabrics more likely to discolor over time and can even weaken the fibers, making them fray and wear out faster.
So that old t-shirt you love might be taking a beating from your water. Which brings us to that age-old question. Why even bother with fabric softener? It sounds like the answer is all about trying to undo the negative effects of hard water.
Exactly. Fabric softeners work by coating the fabric fibers with lubricating chemicals. This counteracts that stiffness caused by the mineral deposits from hard water, making clothes softer and less rough on your skin. And a lot of fabric softeners also help reduce static cling and add a nice scent to your laundry. So they're basically a way to try and overcome some of the annoying side effects of hard water on our clothes.
So we've really delved into the world of hard water today. We've learned that it's mainly about those dissolved calcium and magnesium ions and how they can cause all sorts of trouble, from using more soap to dealing with scale buildup and laundry problems. We've also cleared up the difference between temporary and permanent hardness and looked at some ways to combat these mineral mischief makers. And importantly, we discovered that while hard water might be a pain in the house, it doesn't seem to pose a serious risk to our health.
We've seen how this seemingly simple thing, the hardness of water, can have a big impact on our homes, from how well our cleaning products work to the lifespan of our appliances and even the feel of our clothes. And we've touched on the science behind measuring this property and how the geology of a region shapes its water.
It really makes you think. If something as basic as water hardness can have such a big impact on our lives, what other unseen chemical properties are out there, quietly affecting our daily routines and our homes? It makes you appreciate the complexity of our everyday environment, right? Thanks for joining us on this deep dive today. Don't forget to subscribe to the channel and let us know your thoughts in the comments.